All right. Now this is the video for the additional lecture for the chapter 2.4. It's called the precise definition of limit. All right. So to begin with, you have the intuitive definition, right? Okay. You have this definition. But we need to know, okay, when x is approaching a, x, so when x closer to a or approaching a, we need to know how close x to a. We say that in the intuitive definition, it's really close. But in terms of mathematics, to prove that, we need to have an exact, or a precise number, or in terms of definition, it must be precise. So we still need the precise definition of limit. Okay. All right. So if we have f of x, okay, we have a piecewise functions. First is 2x minus 1. This is if x not equal 3, and this will be 6 if x equal 3. All right. By intuitions, by intuitive definitions, it's clear that when x closer to 3, but x is not 3, the f of x is close to 5. Okay, if you just look at the number here and try to evaluate, this is equal 5. Okay, so the limit is close to 5. Okay, and so by intuitions, we can say we can have this equal 5. Okay, and to ask the precision, how precise the limit is, we need to ask more questions. So how close to 3 does x have to be so that f of x differs from 5? Let's say we must set a specific number that's small, that we can apply this precise definition in all terms of equations. Let's say we have by less than, let's say 0.1. The small gap is 0.1, so we need to have less than that, right? Okay, the distance, then the distance from x to 3 is, and the distance from f of x to 5 is, so our problem is to find a small number. Let's say we need to find, so our problem, okay, let me write, finding a small number, we say delta, small number delta. Let me write in red color, a delta. uh, Let me write, okay, so delta. such that the distance, okay, is less than 0.1. That's the problem asking how close, right? When the distance is less than 0.1. When the distance from the functions to the limit value is less than 1, less than 0.1. Okay. If we have this delta, right? But x is not equal 3. All right. So if this is positive, then x is not equal 3. Okay. So the formulation can be written as, this is the same for the function, and this will be from 0 to less than the distance x minus 3 less than delta. So we need to find the the distance. Okay, so notice that if, okay, 0, okay, let's start with some approximations and some approach for some numbers that is logically makes sense and correct. Let's start with the 0.1 divided by 2. And this is still true, right? This is still true. So we divide this by 2, and then we can also write and exchange the and written the x minus 3 in terms of 2x minus 1 minus 5. So we can write this. This is actually from 2x minus 6. Okay, that is x minus 3 multiplied by 2. And then I can separate them into these 2x minus 1 minus 5. Okay, and then it become 2x minus 3 less than 2. Okay, it's still the same as 0.1, right? And let me move a little bit all this to the upper here. Okay. Maybe make it a little bit smaller. Okay. Now we can make that is if so we find the delta is 0.05. So basically, when you look here, if you think just in terms of mathematics and calculations from the beginning to the end, what you see here is just we work round around, right? Like a circle. So we need to find a delta here, right? And we need to find how to make the conclusion is correct. Okay, so we can imagine that let's say we want to make the 0.1. Okay, let's divide by 2, and this is actually from here we are going to manipulate some number so that we can So we need to write the, so we can assume first, assume that delta is, so we try some number that is true in this case. So in this case, we tried 0.1 divided by 2, okay? Because we know that the functions is actually 2x minus 1, right? So it has to. So probably we try from multiplication by 2 or divide by 2 for the delta, okay? Because the function is multiplied by 2. Okay, let's divide by 2. So by that assumption, we can have that the delta probably 0.05, okay? And then we are going in circle, we find that from the function itself, it's 2x minus 1, right? We try to make this, and obviously it's easy function. It's correct that this is 2x minus 6, which is twice the functions, twice the distance of the delta that we want to find, right? And then if we try to look or observe the 0.05 from here, then it's true that this is going to have 0.1, the number that is we want to observe, okay? So we are going circle in circle, but the idea is we need to find how small the delta is. We need to find the delta. That is precise definition. So if we change, like for example, like how close, let's change to 0.0001. That means in terms of the delta, we need to find the delta that is sufficiently precise for the case of the function. Okay, I hope you get my point here. It seems so confusing because you are going round and round. What we need to find is actually, so we need just to prove this is not finding a number, but this is actually proof when you find a number and you put the number and it's still correct. And that will be the precise definition of limit. Because before we don't really know how much closer that x going to some number a, we don't know, right? But if we are going to apply in a real case, we need to have some assumptions that is, if we are going to use that, we are going to get too close to an exact number, and that is pretty much the precise definition of limit. Okay, okay, let me write in an official way for the definitions. Okay, this is an example that I hope you can get my point from here. Okay, so let's try to work out some official statement for the precise definition of limit. Okay, all right. Okay, uh, oh, maybe before that, let me illustrate what um, this case really is in terms of our uh, visuals. Okay, so we have 2x minus 1, we have 6, we have x is not equal 3 and x equal 3. So a piecewise definition, define functions. Okay, let's try from there. And we start from 3, maybe 1, 2, maybe 3 is here, right? And in terms of a function, we know that this is having a hole here, right? And then having another value equals 6 there. So in terms of limit, we have this equal 5, right? So the limit for the function is 5, okay? And we have another point nearby 3. So where is the delta? The delta is actually the distance between here. So let's say this is 3 minus delta. This is 3 plus delta. So the delta is actually here, the small distance, okay, the delta. So let's say the delta there, and here, usually we call this an epsilon. So this will be the function that we are going to observe, okay? The functions nearby the number 5. Okay, and then this is when this is y x is not equal 3, right? Okay, so this is how the graph illustrate what's happened with the previous problem. Okay, okay, we have delta, we have epsilon. Let's write them in official definitions. Okay, so let me write here precise definition of a limit. Okay, so let a function, let f be a function defined on some open interval that contains number a except possibly at a itself, the definition of limit. Then we say that limit of f of x as x approach uh, approaches a is L. We write this in our intuitive definition, right? So we write this if, okay, there's another additional tax here. So if for every number there is a number delta, okay, so we make a new terms now. We have an epsilon, we have the delta. If 0 then okay, okay, I hope you get the idea behind all of this. Okay, so we need to find actually the delta to know how much x is close to a, right? And then by doing that, we prove that the distance of the functions is less than epsilon. So it's like going forward and backward. And to prove all the things in the function is correct, then if all is fine, all is correct, then the number that we assume it will be our delta. Okay, it will be our delta. All right. Okay. Okay. Let's see what we can do from these definitions, and then we can prove some limit. Okay, and of course, because it's using assumption and proving, usually the case in this precise definition of limit, We are just using it for proving some simple limit that is in our easy to understand why we are doing that. Okay, let me give you an example. Okay, prove limit x equal 3 for x minus 5 is equal 7. All right. The question is not asking how to evaluate the limit, because evaluate the limit, you know the limit for this one is 7, right? But how to prove that? Now we need to have our idea about delta and epsilon and make it happen here and make it equal and then prove that the limit is true, right? Okay. So first let epsilon is positive. Uh, finding delta such that and then okay. Now this is what does it mean is we need to understand the x minus 3 here. This is the distance, right? The how close x to 3, right? So from here, from x approaching 3, we are going to find how close that is, and we are going to mark that distance with the delta. Okay, and we have also a function with its L. So this is f of x, this is L, right? And we are going to use the delta to prove that when when it is in the functions like this, it is less than its epsilon. Okay. All right. From here is actually we can move from the epsilon first. For example, this is the case from here. Okay. Let's simplify this, become this one, and we know that this is actually 4 times of x minus 3, right? Therefore, okay, we want delta such that if 0, then now because it was such an easy limit, we know that from here we can make some conclusion, right? We can make some relations. X minus 3 is already in a common element there, right? X minus 3. So if we want this to be true, if we want this to be true, then we can select the delta to be epsilon over 4. Then suggest delta is epsilon over 4. And then this is the second part. So the first part, this is analysis. Okay, we try to find um, which part are going to be a suggestions, which part, which delta we need to take. Okay, and after we get okay, maybe the delta need to be half an epsilon over 4, then we need to prove that. Proof. Okay. So given epsilon greater than 0, choose delta epsilon over 4. Okay. So if and then we prove that, and we are going to plug in into our solution here. And we are going to have this becoming this. And of course, this will be 4, epsilon over 4. And it is true that it's become the epsilon that we want to prove. Okay. So conclusion thus, if 0, then this is true. Therefore, if you want to write completely, therefore, uh, this equals 7. Okay, I hope you get the idea of the how we are going to use this precise definition of limit. Okay, and of course, precise definition of limit is not limited on some of the theorem. It's most of the theorem in limit we can have its precise definitions. Okay, so for example, for one-side limit, we have also the precise definition. So let's move on to the one-side limit. You can pause and then go back and then relearn and maybe read one more if you still confused about the precise definition. Okay, so one-side limit. So if you have a limit x approaching a from the left, this is the definitions, right, for a left-hand limit. Okay, so if for every number epsilon greater 0, there is a number delta which is positive, such that and then you have also, and you can also have the other one from the right, same, such that if, because it's from the right, now we have from a less x less a plus delta, then all right. Okay, one more theorem about infinite limit. So infinite limit, so we have definition at the definition of the infinite limit, right? So this means that for every positive number m, there is positive number delta, such that if 0, then we have f of x greater than m. What is m? Let me write here, maybe draw here. Okay, let me draw here how it looks like. So maybe like that, going up. Okay. And let me make the asymptote here. Okay, make it a little bit middle in the middle. And let's say we have, let's say we have the y equal m here, and we have the asymptote x equal a here, right? What the m is actually, it's actually, we have some distance here. This is a minus delta. This is a plus delta. And this will be our m here, okay? So we have the distance, delta, and our functions is getting larger and larger and larger, and it is overcome, or it is moving forward the y equal m. Okay, so m is just in the terms of delta epsilon m, so it's every number, every positive number, then when you put there, the function is still greater than m. Okay, okay, so the other way around, if you have the other infinite limit, okay, so if you have limit x approaching a and it's getting negatively large, so this will be true uh, for every negative number n. There is positive number delta such that, or maybe right then, and it is similar with m, but it is on the negative side. Let's say that is the n, okay, and this will be the asymptote. So this will be a, okay, this will be a, this will be a minus delta, this will be a plus delta, okay, and this green line will be our y equal n. Okay. So the functions is, of course, is getting negatively large, or getting smaller and smaller, getting to the going down and less than the n. Okay, the y equal n, right? Okay, I hope you get my idea here. Uh, the precise definition of limit, and you can also apply for the one side limit, and also you can apply for the infinite limit. And I hope at least, okay, at least you get the idea how to prove this example. Okay, this really easy limit, and you can understand how to use the precise definition of limit to prove that the limit is true. Okay, okay. So if you are still confused, you can start um, rewatch the video, and then you can also look for some um, another example if you want. And if we have time in the future, I will also maybe in the class giving you another example. Okay, so I think this will be the video about the precise definition of limit.